Hi guys, welcome to the stream on equivalence relations and partial orders. Today we'll be building up from what we looked at relations the last time around, which in turn is a build up from sets, and that in turn is a build up from predicate logic as well as propositional logic. So it all builds up. So if you want to check out some of those other topics, you can go click on the other videos in the channel. They're all online, they're all available for your viewing pleasure. So feel free to take a look at that if you wish. So we're going to sort of rebuild or scratch that. We're going to pick up from where we last left off in terms of relations. So let's first start with the first question. And we have a set A. We are given this particular relation on A. So we'll define the relation by the following collection of connections from one item to another item. So we're gonna AA, AB, AC. We're gonna go to BA, and I'm going to use this column sort of array notation, matrix notation, if you would, just so that it's easier to keep track of what's going on. So BC, CA, CB, CC, DE, DD and EE. So we're given this relation, this is what the question gives us. And the first line of business is to represent this using an arrow diagram. So that raises the question, how exactly do we draw that? Just like before, we can put in our nodes A, B, C, D, because the set of consideration is A, which consists of the items A, B, C, D, and E. So we'll put A, B, C, D, and E. I believe there are a few other ways you could represent that, but this is fine, this works, it gets the job done. Totally fine, it's all good. So let's mark down one of each of those connections one at a time. So A is connected to itself. You get this looping feature over here. In fact, BB, all of the letters are actually, there's a relation between a letter and itself. So every item is connected to itself. So you have all of these little loops over here. Secondly, we see that A is connected to B, and at the same time we also have B being connected to A. Next up, we have A being connected to C, and C being connected to A. So A being connected to C looks a bit like this, C being connected to A. And B being connected to C looks like this, and C being connected to B. So those are pretty much all of the different connections that we could possibly make that represents this relation. But the next question is a little bit more abstract, because now we're asked about an equivalence relation. So what do we mean by an equivalence relation? So let's first define a bunch of things before we even write down the question. Let's define a bunch of things. We'll say that a relation on A is, we can describe this relation in a few different ways. So the first thing is, the first way to describe it is reflexivity. The second way to describe it is symmetry. The third way to describe it is anti-symmetry. And the fourth way to describe it is transitivity. And these are rather big words, but these are relatively commonly used in discussing relations, so it's best to know, or at least acquaint ourselves with the vocabulary therein. But what do these words mean? Right, so that's the question. Well, let's start with the first one. A relation is reflexive when, no matter which item you choose, you can always connect the item to itself. In other words, the relation x to x belongs there. For any item you wish, you always can have the connection from an item to itself. In a diagram, it actually looks like loops. So in other words, another way of saying it informally is that every node or point or whatever you want, node, point, vertex, has a loop. This is the informal way of saying it, but it does help to visualize the situation. And in this situation, we can see that what we have here, we'll call this situation here, let's just call this star. We'll call this star. We can see that actually star has a loop at every point. We actually do get loops. So therefore, the star is reflexive. Right? So in that sense. Now, strictly speaking, it's R, but we can change it to star. Let me just easily change it to star. Define the relation star. There we go. Look at that. Now we can say that star is indeed reflexive. So what does symmetry mean? Symmetry has this rather slightly more complicated definition, but we'll get used to it. So we'll say that R is symmetric if for any items you wish, they may be the same item, we don't know, and honestly, we don't really care. If one item is connected to the other item, then if you were to flip it around, we had better have a connection in the reverse direction. So I like to think of this as two-way streets. Every street, in other words, if you have a street, it has to be two-way. So in this situation, let's look at the relation star here once again. Let's consider the street A to B. The question remains, does B to A lie inside the relation? And the answer is, well, yes, it's there. And vice versa. We also include loops because a loop can be treated as a two-way street. Well, A to A is the same as A to A. It's actually the same loop, even though if we were to draw it on the piece of paper, it looks sort of different. But as far as the relation is concerned, these two connections are the same around a single point. Of course, A to B is completely different from B to A because the points are different. But when the points are same, we can go either clockwise or anti-clockwise. It's not that big of a deal. In that regard, we can regard loops as two-way streets. So I like to call this every street is two-way. And loops are two-way as well. Loops are considered to be two-way streets. So now we just need to check that every street is a two-way street. So let's see. Is this two ways? Well, yes, there's a two-way street there. Is this a two-way street? There's two ways. Is this two ways? Yes. And every other street is a loop, which is two-way. So in that sense, you can say that the relation is symmetric. Now we'll come to anti-symmetry in a moment, but let's look at the next one called transitivity. So transitivity comes from the word transit, which basically means you can go one step at a time, right? So here's the formal definition, and I like to think of another analogy for this, so stay tuned for that. So we say that the relation is transitive if for any three items, and these could be the same item, I'm not saying that they are the same, but they could be the same. If you have two items that are connected from X to Y, and two items that are connected this time from Y to X, you can basically treat Y as a bridge. You should have that X is connected to Z. That's what we want to convey. So I like to think of it this way. If I am currently in Singapore and I want to travel to Thailand via bus or land or whatever, train, all that good stuff, I can take a stopover at Malaysia. I don't know why I spelled this one full and the others in abbreviations. I'm not too sure. But in either case, if I can travel from Singapore to Malaysia, and I can travel from Malaysia to Thailand, right? So let's try that again. Singapore, Malaysia, Thailand. If I can travel from Singapore to Malaysia, and I can travel from Malaysia to Thailand, in that sense, I can regard this as a travel from Singapore to Thailand. I'm transiting in Malaysia. In that sense, this is transitive. So here's how I like to think about it. Every pair of roads is transitable. Every pair of roads can transit. So every pair of roads can transit. In some sense, this sort of conveys the idea of sameness, but we'll look at that in a moment. So let's take a look. For the road A to B and the road B to A, we're going from A to B and B to A. So the start is A and the final is A as well. Do we have a connection from A to A? Yes, we do. We actually do have a connection from A to A. Now what about A to B and B to C? So A to B and B to C. The starting is A, we transit in B, and we end up at C. Can we actually go from A to C direct? Well, yes, we have this connection here. So we can actually check that every pair of roads, the middle guy can be treated as a bridge. You can actually go from the start to the end inside the relation as well. So in that sense, we can say that star is transitive. And we'll come to anti-symmetry in a moment because we want to talk about this other idea of a partial order in just a moment. But if we think about the idea of reflexivity, symmetry, and transitivity, these agree a lot with our ideas of sameness. Okay, so what do I mean by sameness? So we'll define R is an equivalence relation on the set A if it satisfies three things. If firstly, R is reflexive. Secondly, R is symmetric. And finally, R is transitive. So I'm going to explain why equivalence relations require these three ideas. Now, equivalence relations, roughly speaking, is a way to generalize sameness. So because we are thinking about equivalence, so things that are in some sense the same as one another. So what are some of the ideas that we want to bring out from this idea of sameness? Well, if we treat two items as the same, ideally, every item should be the same as itself. It should be the same as itself. In that sense, it has to be reflective. Every item should be the same as or related to itself. It should be the same as itself. Secondly, if the cross is thus treated as the same as the triangle, then by our ideas of sameness, we would like to treat the triangle the same as the cross. In that regard, the sameness should go both ways. It should be a two-way street. And that's why we have sameness satisfying symmetry. Finally, let's just say we have a cross, a triangle, and a circle. If the cross and the triangle are treated as the same, and the triangle and the circle are treated as the same, then in some sense, the cross ought to be treated as the same as the circle. In that sense, sameness should be able to be transited, right? We should be able to use the triangle as a bridge to talk about sameness between the cross and the circle. In that regard, sameness ought to be reflexive because every item is the same as itself, symmetric because sameness should go both ways, and transitive because sameness should be transferable. I think, in fact, that might be a better way to think about transitivity. We can think of it as transferring, right? So that's the idea of equivalence relations. So this tells us, since the star is reflexive, because every item is connected to itself, since the star is symmetric, since every road is two-way, and since star is transitive, because every road can be transferred, we can say that star, and this is actually part B of the question, star is an equivalence relation. And sometimes I'm just gonna abbreviate equivalence relation with the letters ER, because math people are really, really lazy. So that is the idea. And we can ask ourselves, what are its equivalence classes? Let's first copy and paste this diagram. And we want to ask, what are the equivalence classes? So question, this is actually part of the same question. What are the equivalence classes of star? And well, the first thing to ask is, what exactly do we mean by equivalence classes? Now, because star is an equivalence relation, we can in some sense treat these items with this generalized sameness. So we can put them all into the same box and treat all of these items, as far as being part of the box is concerned, they are all essentially the same thing. Essentially here means with respect to star. In general, A is not B and B is not C. That's just not generally the case. But under this set of connections, we can treat them as the same, because star is reflexive, symmetric, and transitive. We can treat items that are connected to one another as the same. So, firstly, let's define an equivalence class. So the equivalence class, in fact, before we talk about equivalence classes, we ought to have a equivalence relation. So we will usually the notation for equivalence relation is tilde. Let tilde be an equivalence relation on a set A. Then the equivalence class containing X, and we will usually represent this with the symbol, the square bracket, X tilde. So what this tells us, this symbol here sort of helps us clarify what we mean. We're saying that we're talking about the equivalence class containing X when we consider this particular equivalence relation. Different collections of arrows give us different relations, and they give us different equivalence relations. So there are many different possible equivalence relations, as long as they satisfy reflexivity, symmetry, and transitivity. Within that context of that equivalence relation, items that are connected are treated as the same. Takes a bit of getting used to, but we will get used to it with enough time and practice. So the equivalence class containing A is defined by this symbol, or as this symbol. But what does it contain? What are the items that it contains? It will contain all the other items that are connected to X. This is what it means. So an equivalence class that contains X is the collection of all the different things that are connected to X. So that's the idea there. And we are going to ask what the equivalence classes of star technically, the answer here, what are the equivalence classes? Well, it's basically all of these guys. These are all the different possible equivalence classes we could obtain, because A consists of the points A, B, C, D, E. So all the different possible equivalence classes are simply these guys. Let's make it a little bit more interesting. Let's say we want to find it in roster notation. Let's just say we want to do it in roster notation rather than just in general. Now, if we want to look at it in roster notation, we need to ask ourselves, what are all the items that are related to A? From our diagram, these are all the items that are, all the points, items, nodes, whatever you want to call it, that are connected to A. And in this situation, we have B being connected to A and C being connected to A. So we can put A, and A is obviously connected to itself, right? A is actually connected to itself. So A is connected to itself, B is connected to A, and C is also connected to A. Now what about the equivalence class containing B? That has to contain B, but if it contains B, it must contain A, because A is connected to B, and it must contain C, because C is connected to B. So we are actually going to get the same set over here, as well as here. B, the equivalence class containing B is the same as the equivalence class containing A. It's the same as the equivalence class containing C, because A, B, and C are really all related to each other. And the equivalence class containing D is on its own island. It's not connected to anything else, so we're just gonna put D on its little island on its own. Same thing with the set containing E. So these are what we call the equivalence classes of the set with respect to the equivalence relation. If you have a different equivalence relation, you get different equivalence classes. Now, another question will be to ask if it is a partial order. And to answer this question, once again, just like the equivalence relation question, we need to figure out what exactly do we mean by a partial order. So let me replicate the different conditions and see what's missing. We've seen these definitions before. Reflexivity means that every point has a loop. Symmetry means that every road is two ways. And in this situation, we will consider loops as two-way roads as well, two-way streets. And transitive means we can transfer from one point to another. There is one property called anti-symmetry, which I'm going to write the proper definition here. We actually covered this in one of our previous videos and streams on predicate logic. So if you want to check that out, feel free to go and take a look at that. So anti-symmetry says this: for any 2 points, and there are multiple ways to phrase this, but I'm going to use this phrasing because it's sort of the useful way to think about. For any 2 points, suppose these 2 points are indeed connected to one another. Let's suppose this is the case. Anti-symmetry is a bit annoying. They say that if you have 2 streets between 2 points, turns out that the only possibility is that if they are one and the same. That's the only possibility for anti-symmetry. This might be a bit confusing, like, wait, what's going on here? So the idea here is that before we talk about anti-symmetry, let's first talk about partial orders. Now, just like equivalence relations generalize equality, partial orders will generalize inequality. It's a generalized way of sort of arranging things in a sequence. So we can think about that and ask ourselves a similar question. If we consider a number, say m, and we ask, well, what numbers will it be smaller than or equals to? Surely we must require that m is smaller than or equal to itself. Right? That's one of the key ideas of the integers. And furthermore, suppose we have m being less than or equals to n, and n being less than or equal to, say, r. I don't know why I chose these letters. Then in some sense, if m is smaller than or equals to n, and n is smaller than or equals to r, what do we want to conclude? We would like to conclude that m is smaller than or equals to r, right? In other words, the smaller than or equals to property can be transferred. In other words, in the less than equals to probably will require reflexivity as well as transitivity. But then what then makes it any different with just equals? Well, here's a little bit over here. If m is smaller than or equals to n, and n is smaller than or equals to m, what conclusion can we make? If m is not bigger than n, but at the same time n is not bigger than m, then we must conclude that the two numbers actually are one and the same, right? Two-way less than or equals to will get the same number. This is precisely what we mean by anti-symmetry. If there is a connection from left to right and a connection from right to left, it turns out the left and right actually have to be the same guy. So that's the idea. And pictorially, what does it look like? I like to think of it this way. Every street is one way. And we'll say that loops are one way. So loops are special. They sort of can play the role of both a two-way street and a one-way street. And in this situation, we see that we have a street here that is two ways. So we can conclude that star does not satisfy anti-symmetry. Well, because star has a two-way street. That is not a loop, right? The only two-way streets we allow for anti-symmetry are loops. Everything else has to be one way. You can think of anti-symmetry in that way. Now what it tells us is that, well, what's a partial order? We can now define a partial order properly as well. A partial order is a relation. Well, we usually say a partial order on a set. It's a relation on a set that is reflexive because we want to have a number being smaller than or equal to itself. Anti-symmetric and transitive. That's what we mean by a partial order. And since star is not anti-symmetric, we violated one condition. We can conclude that star is not a partial order because it violates one of the conditions. If we want to show that it is a partial order, we need to show that it satisfies all three conditions. And if we want to show that it's not a partial order, we just need to violate one of them. We have another question which is a little bit tricky as well, but bear with me. Is star a total order? That's the question. Is star a total order? Well, the first thing is, what do we mean by a total order? Right? So one thing is for sure is that star is not a partial order. So just by the English, we can probably conclude he's probably not a total order, right? But what exactly is a total order? So a little bit of terminology today, but we'll get there. It's fine. We'll say that a relation R on A is a total order if it satisfies two conditions. The first condition is that it has to be a partial order. And the second condition takes a little bit of effort to define. And there's a word to describe this. But roughly speaking, I'm just going to put it out here. For any two items, X and Y are comparable. I'll detail this in just a moment. But since star is not even a partial order, and to be a total order, you actually need both partial order and this comparability property, which is going to take some effort to describe. We can conclude that star is not a total order. We can say that this is the case because star is not a partial order. Also, I'm probably gonna abbreviate partial orders in the future with PO, just because it's shorter and math people are really lazy. That shouldn't surprise any of you. Now, before we continue on with equivalence relations, let's first discuss this notion of comparability. What exactly do we mean by comparable here, and why does that give us a total order? So, the best way I can think of is to describe a situation where we can see this idea in action. So let's consider a few things. We'll say that we'll consider this idea here. So we'll consider this guy 1, 2, and 6. Okay, and we're gonna draw an arrow. We'll draw an arrow. So we'll draw an arrow, connect X to Y if X is a factor of Y. So if Y divided by X gives us some integer. So let's see what happens. Well, clearly all these items are factors of themselves. 1 is a factor of itself, 2 is a factor of itself, and 6 is a factor of itself. I won't be proving this in this particular scenario, but just an intuitive picture here, because every number, if you divide by itself, you're going to get the integer 1. Furthermore, we know that 1 is a factor of 2 and 1 is a factor of 6. And we also know that 2 is a factor of 6. So let's check that, is this guy a partial order? Well, partial order, so my question now is, we call this relation S, right? Let's just call this relation S. So let's see, is S a partial order? And the idea here is that, well, let's just check. Does every item have a loop? Well, yes, every item in here has a loop, right? So yes, it is reflexive. It is reflexive. S is reflexive. Are all of the different streets transferable? So let's just say 1 to 2 and 2 to 6. Can we go from 1 to 6? No, yeah, there. And if we go from 1 to 1 and 1 to 2, can we go from 1 to 2? Well, of course, 1 to 2 is here. So we do see that we do get this street transferability property, so it is transitive. And finally, my last question to ask is, are all of the streets one-way streets? Well, loops are treated as one-way, so that's fine. And all of the remaining streets only go in one direction. You don't ever see the reverse, right? You have 2 to 6 here, but you do not see 6 to 2. And similarly, you do not see 6 to 1, which makes sense because you can't divide 1 by 6 and get an integer, because 6 is strictly bigger than 1. So we do get anti-symmetry as well. So that establishes that S is a partial order. And furthermore, and this is what we mean by comparable, we say that x and y are comparable precisely when there is at least one connection. Right? There is at least one connection. It means that xy in S or yx in S. In other words, between any 2 points, there is at least one connection. So let's take a look. Is there a connection between 1 and 2? Well, yes. Is there a connection between 2 and 6? Yes. Is there a connection between 1 and 6? Yes. And is there a connection between any point and itself? Well, it better have, because that allows it to be reflexive, right? So in this situation, S is not just a partial order, but S also satisfies the comparability property. Since for any xy in 1, 2, 3, xy is comparable, which now we can think of is at least one street. Anti-symmetry tells us at most one street. Since for any xy is comparable, we have that S is a total order. S will be a total order. Now, what then makes it different from a partial order? I mean, we've just seen a partial order, we've seen total order, what's the point? Well, what if we now considered a very similar relation, but not exactly the same? Now let's consider another point 3. Once again, we connect if we get the item being a factor. So if 1 is a factor of 3, we can connect them. So we can do that. We can connect 3 to 6. We can connect 3 to itself. We do not connect 3 to 2. And you can check that this will still give us a partial order, because every point still has a loop to itself. All streets are transferable, and every street is one way if you treat loops as one ways. But however, this does not satisfy the comparability property. The reason here is because 2 and 3, are there any streets between 2 and 3? No, there are no streets between 2 and 3, because 2 is not a factor of 3, otherwise 3 will be even, a contradiction. And 3 cannot be a factor of 2 because 3 is bigger than 2. Now what it tells us, therefore, is that this new modified, I guess I can call it S prime, is a partial order, but not a total order. And the reason that S prime, if you would, is not a total order is because 2 and 3 are not comparable. And that's a subtle difference between comparability, between a total order and partial order, is this added condition of comparability. I believe the importance of comparability is because we want to talk about this idea of a topological sort. Not a big issue, but that is one of the key differences between a partial order and a total order. So just a subtle difference there. Fundamentally, I guess we could sort of wrap up our discussion here. We have a relation. We can say that it has a bunch of properties, if you would. We can say reflexivity, means it contains all of its loops. Symmetry, all the streets are two-way, and you treat loops as two ways. Anti-symmetry, which means that all the streets are one way, and you do count loops as one way. Finally, transitivity, which tells us that connections are transferable. And we say that R is an equivalence relation and a partial order if it satisfies some properties. It's an equivalence relation if it satisfies reflexivity, symmetry, and transitivity. It's a partial order if it satisfies reflexivity, anti-symmetry, and transitivity. These do make sense if we think about equivalence relations as sameness and partial order as less than equals to. Finally, we say that R is a total order if and only if R is a partial order and for every item, every pair of items are comparable. All pairs of points, and we allow the pairs to be the same, have at least one connection. This is where we can more precisely say all pairs of points are comparable. There's a subtle difference between total order and partial order. Otherwise, that's basically the key terminology, if you would. There is quite a bit of new terminology this time around compared to the previous one. So we will practice more and get used to seeing how to work with these ideas in just a moment. Okay, let's practice. Let's practice on reflexivity, symmetry, anti-symmetry, and all of that with this next question. Let's ask which are the following relations R and S reflexive, symmetric, anti-symmetric, or transitive. So let's slowly check. But what exactly is R and S, right? So we need to know what's the question before we can start. R is gonna be the relation defined by connecting two rational numbers with the property that if you multiply them, you're gonna get a non-negative number. So let's check. Let's check each of these conditions. Let's check reflexivity. Let's fix any item and ask ourselves, do we get the property x comma x inside q squared? Do we have this? And let's unpack this using the definition. It means that x times x is bigger than or equal to 0. Do we have this property? Well, effectively this is actually x squared bigger than or equals to 0, and we've actually proved this result a while back. We actually proved that if you take the square of any rational number, you will get a number that is non-negative. So let's go ahead to establish the result. Since x squared will be bigger than or equal to 0, we can conclude that x times x will be bigger than or equal to 0. That tells us that xy, well, not xy, xx actually belongs to R. X and x are connected, and therefore we have R being reflexive. So R is reflexive. Or maybe we'll write it here. Therefore, R is reflexive. Well, we have a few more properties. Let's go take a look at them. So what about symmetry? What about symmetry? Well, symmetry asks us to check whether or not, well, for any two items, they could be the same. We do not know, and honestly, we do not really care. We want to start off supposing that x and y lie in the relation. Our question that we want to ask is, if we were to swap the y and x's, in other words, if we were to have a mirror, symmetric, does this still lie inside R? That's the question, right? These are all questions. And we can unpack this to mean that y multiplied by x ought to be non-negative. And we do know that if xy is in R, then by definition, xy has to be non-negative. But xy and yx, because multiplication of rational numbers is swappable, it is commutative, we do get yx bigger than or equal to 0, which means that yx does belong to R, which tells us that R is symmetric. We do get the symmetry property there. Now, what about anti-symmetry? Let's provide some more space here. What about anti-symmetry? Anti-symmetry tells us that for any 2 points, if they are connected to one another and both are connected, well, if 2 items are connected and the flip version are also connected, then it must be the same items. But we've seen from the symmetry side that this is probably not the case because we have a lot of items to choose from in the rational numbers. So let's choose some numbers where we choose x equals to 1 and y equals to 2, and they're not the same, right? X is not equals to y. Then we can actually check that xy, which is 1 times 2, is non-negative, and yx, which is 2 times 1, is also non-negative. We have the symmetry property actually. But that tells us that xy belongs to the relation and yx belongs to the relation. So we've actually found 2 items, and yet we have this two-way street property. If we were to sort of draw it out, not very precisely, but somewhat illustrating the point, we can find 2 points with a two-way street, which is not a loop. Therefore, R is not anti-symmetric. Can't be, we have a two-way street here. Let's give it some space. Finally, we can ask the question on transitivity. And this question here is this idea that if x and y is non-negative, or rather if xy, okay, let's just fix the definition, fix x, y, z in Q, we suppose that x, y are connected and y, z are connected. The question here is, are x, z necessarily connected to each other? Well, we could try to decode this and see what we get. The first one, the top there tells us that xz is non-negative. The one on the bottom tells us that xy is non-negative. And yz being in R tells us that yz is non-negative. And this raises a little bit of a question mark, because how exactly do we think about this? In fact, I think the answer here is no. I think the answer here is it's not the case. Now, if here's my idea. If y, well, let's take a look. Once you have xy and yz being non-negative, you could actually multiply the 2 terms together and you're gonna get xy squared z is non-negative. And if you know that your bridge is non-zero, you're dividing out a positive number, you actually can conclude that xz is positive, non-negative. You actually can conclude this because if you're dividing by a positive number, the symbol in the bigger than or equal to symbol does not change. So actually we are good to go, except the possibility that y might be equal to 0. That could throw a wrench in many of our plans, and it does. So here's my argument. So my claim is that R is not transitive. And here's my justification. We'll choose x to be a negative number, y to be 0. Now if y is non-zero, actually we cannot really disprove anything, but the key idea is that y is equal to 0 here. And z equals to 1. Why do I want that property? Then we have xy being negative 1 times 0, which is 0. Yz being 0 times 1, which is 0. And therefore, well, and xz being minus 1 times 1, which is negative 1, is actually less than 0. But what this means is that x and y are related, y and z are related. However, xz is not related. In other words, even though we can go from x to y to z, we can do this, we can't actually go from x to z. Sadly, this is not within our travel itinerary. Unfortunately, we can't do this. So in fact, R is not transitive. So as far as R is concerned, R is reflexive and symmetric, but it is not anti-symmetric and it is not transitive. We're going to repeat the same question, but now with S instead of R. And what is S? We have to write that down in proper detail. We want to answer these same questions as before. We want to ask whether the relation S is reflexive, symmetric, anti-symmetric, and transitive. And let's just write out what S is in this context. S is going to be the collection of pairs, connections between pairs, such that x1 is smaller than or equal to x2 and y1 is smaller than or equals to y2. Perhaps a picture might help us represent this idea. Over here we have, well, not S, r squared times r squared. And the idea here is that x1, y1 is a point in r squared, x2, y2 is a point in r squared. How do we connect these points? We'll connect the points, we'll draw an arrow if one is sort of higher and further away than the other, right? In the right direction and up direction as well. That captures the idea of x1 being smaller than x2 and y1 being smaller than or equals to y2. Can be the same, it's fine as well. This should sort of let us think it's probably going to be a partial order-ish, because there is this natural, ordering over here. So there is a chance it's a partial order. We are not sure. We're going to have to take a look. But that's just a hunch. Now let's check that. Well, let's see. For S, is it reflexive? How do we check if S is reflexive? We'll need to fix any item in S. And the items here now are points. So let's write it as y, x1, x and y. Alright, let's fix that. And we need to ask the question, is S reflexive? And what that means is, well, here's the question. Is xy, comma xy, does this pair, is the point xy connected to itself? Right? Well, we need to unpack that information. What that would mean is that x is smaller than or equal to x and y is smaller than or equal to y. That's true, right? Because of the real numbers property. Well, since x and y are real numbers, x is less than or equal to x and y is less than or equals to y. These two pieces of information will give us that xy is connected to itself, which means that S is reflexive. Okay, I don't think it's symmetric, because the idea is you can go this way, but you probably can't go this way, right? Because if you go this way, then you can only go towards the right. The idea is you can only go towards the right and up. You can't go down. So that's sort of the mental picture I have. And we can come up with a really simple counterexample here. We will consider the point 0, 0 in R squared and 1, 1 in R squared. Then we know that 0 is less than or equals to 1 in both coordinates, which tells us that 0, 0 and 1, 1 are connected. And yet, 1 cannot be smaller than or equal to 0. Obviously not. Which tells us that 1, 1 and 0, 0 cannot be in S. Because 1 is clearly strictly bigger than 0. Within the real numbers, that works. So we have a situation where we can go from 0 to 1, 1, but not the other way around. The street is not two-way. Which means that S is not symmetric. S cannot be symmetric. Let's make some space to check the other properties. We want to check whether S is transitive, well not transitive, anti-symmetric or not. So let's just check anti-symmetry. And roughly speaking, the idea is sort of between any 2 points you probably will get, well, between any 2 points, the streets can only be one way, roughly speaking. That's sort of the idea. Let's try to demonstrate that to be the case. So if we do get two-way streets, we can only get loops. And let's do that. Let's fix the points x1, y1 and x2, y2 in the two-dimensional plane. Let's suppose that we do get both connections in two directions. So we do get this connection and this connection. Again, our idea here is to sort of eventually show that x1 and x2 must actually be the same. They must actually be one and the same. Same with y1 and y2. Because you can only have one-way streets, roughly speaking. We can unpack this to mean that the x-coordinates here, the left one is smaller than the right one, and that the y-coordinate also satisfies a similar property. And we can derive a similar pair of inequalities on the right side. We are just going by the definition of S over here. So we do have all of these different ideas here, and the fact that we have x1 and x2 like this is really, really interesting, and there are actually ways to generalize this idea, but it's fine. This is interesting because if x1 is smaller than or equals to x2, and x2 is smaller than or equals to x1, these two pieces of information have to combine to give us x1 being equal to x2. That must be the case, because we have this two-way less than equals to property, so they have to be the same number. And likewise with the y1, y2s. This will give us the fact that y1 equals to y2. But if we combine these properties together, we are going to get the fact that the point x1, y1 really is the same as the point y1, x2, y2. These points are really one and the same. But if you start from these connections to derive that we have that these two items are one and the same, we must have anti-symmetry. So therefore, S is anti-symmetric. Let's make space to check out transitivity. Finally, let's check if S is transitive. So pictorial looks a bit like this. If we do get this non-decreasing connection, we should be able to get a non-decreasing connection this way. So just from the diagram, we sort of have a hunch that S is probably transitive. Probably. But let's go ahead and prove it. So let's fix 3 points. And again, there could be a repeated pair of points, but it's fine. In the Cartesian product. And we'll suppose that we have these two connected and these two connected. Our idea is that these two guys are probably going to be connected. Probably. Now, there is actually a theory as to why this works, and I might talk about it in the future. But for now, we're just going to work with what we have here. So, what does this tell us? If we do get these connections, the definition tells us that x1 has to be smaller than or equals to x2, and y1 has to be smaller than or equals to y2. On the other hand, over here, x2 has to be smaller than x3, and y1 has to be smaller than or equals to, well, y2 has to be smaller than or equals to y3. Now, just like the previous situation with anti-symmetry, we can combine some information about the less than or equals to symbols, in which this tells us that we actually do get x1 being less than or equals to x3. Similarly, these two pieces of information here help us derive that y1 is smaller than or equals to y2, and that's smaller than or equals to y3, so we get smaller than or equals to y3. These two things both hold at the same time, so this actually helps us conclude that x1, y1 is connected to x3, y3. But since we've shown that these two guys are connected, or rather, since this and this being connected tells us that the beginning and the end are connected, we can conclude that S is anti-symmetric. Well, not anti-symmetric, sorry. That was wrong. Transitive. Now we can do something even more interesting, right? We can do some interesting ideas over here as well. And the fact of the matter is we can show, well, we have the fact that S is reflexive, anti-symmetric, and transitive. We can actually conclude that S is a partial order. And furthermore, we can actually conclude that S... No, we can't conclude that S is a total order. I don't think we can conclude that S is a total order, because we can find 2 points in the plane, such as these 2 points. There's no connection between them. You can't find connections. So we don't get total order. But we do get S being a partial order, and that is how we derive that. We deduce that information because S is reflexive, anti-symmetric, and transitive. Let's go ahead to prove some results about equivalence relations. We'll define the relation R on R squared via the following definition. 2 points are connected under the condition that this equation is satisfied. And that looks kind of strange, like, wait, this is the collection of connections? Well, it is. Well, it's r squared times r squared, pardon me. So we are going to connect 2 points like this if they satisfy this equation. That's the idea. We're going to connect the 2 points if they satisfy the equation. And we are required to check with the claim here is that R is an equivalence relation, which I'll usually abbreviate using ER. What does it mean for R to be an equivalence relation? We've seen previously that an equivalence relation is a relation that satisfies 3 properties. We have reflexivity, symmetry, and transitivity. We need to prove that R satisfies all of these 3 properties. By the way, it's kind of nice that it's R, S, and T. It's like consecutive letters in the alphabet. I thought that's quite cool, so fair enough. I don't know if the mathematicians who thought of this intended this to be the case, but it's fine. So we claim that R is an equivalence relation, so let's go ahead and prove this claim. Now, to prove that R is an equivalence relation, we need to show that R is reflexive, symmetric, and transitive. So to show that R is reflexive, how do we go about it? Well, we need to fix a point in R square. Why R squared? Because we are defining R on R squared. And we claim that our goal is to show that xy is connected to xy. That's our goal. That's what reflexivity means. Any point you want will be connected to itself. So let's maybe unpack the definition here. What does it mean if that's the situation? It means that 3 of x minus x ought to be equal to y minus y, which makes sense, right? It makes sense because this goes to 0 and this goes to 0. So how do we demonstrate this in the proof? Then, since x and y are points here, so they're real numbers, right? We can say that 3x minus x, well, 3 times x minus x is 0, and y minus y is 0. So we get that 3x minus x is equal to y minus y, which is this equation, which tells us that xy are in fact related to one another. So that's the element over there. That's for reflexivity. And that's sort of an important way of thinking because it's not as direct. It's not just boom, 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 we're good to go. Now, some of us who are familiar with that, more power to you. But for some of us who are not as familiar with math proving, there really is a strategy involved. Sometimes you start with the end in mind and you work your way towards the end. So that's entirely possible as well. For symmetry, we probably need some space. Give me a moment. For symmetry, we actually need to do a bit of work, so we'll fix 2 points. Over here, we are going to suppose that they are connected. I wrote a typo here. This should be 2 points in the 2D plane. Suppose that they are connected. Our goal is to show that if you were to flip the points, in other words, instead of the first and the second point, you get the second and the first point. You do get them still connected to each other. So let's see what we can do here. We start off with the first guy. So the first one tells us that 3 times of x1 minus x2 is going to be equal to x well, y1 minus y2. And the goal that we have to show is that 3 of x2 minus x1 is equal to y2 minus y1. And this looks almost like we're done because you just need to flip the symbols, right? So let's just put a negative sign in front of everything. This is still legit. And this actually gives us, we can flip the x1 minus x2 into x2 minus x1 by algebra. And we're good to go. That's that. So therefore, R is symmetric. I think we've proved that, so that's fine. Let's make space for transitivity. Let's now show that R is transitive. To show that R is transitive, we need to fix 3 points. And we need to make 2 suppositions. We suppose that the first 2 points are connected. We suppose the second 2 points are connected. Well, the second and the third points are connected. I do not know why I use Z here. This should still be. This is very bad notation. Give me a moment. Let's do that again. So we want to suppose that these 2 things are connected. What do we want to show? We want to show that the first guy and the third guy are connected as well. The connection is transferable. It's transitive. So let's unpack each of the definitions and hope for the best. The first guy tells us that 3 of the difference in the x coordinates will be equal to y, the difference in the y coordinates. Similar to this guy, so let's just use the conjunction and. And our goal is to show that 3 of x1 minus x3 is equal to y1 minus y3. Sometimes it feels like we're going to get stuck, but then we need to ask ourselves, wait a minute, this equation and this equation, this y1 minus y2 and this y2 minus y3, if we added them together, we're going to get y1 minus y3. We're going to get y1 minus y3 because these 2 y2s will cancel out if we add them together. So what if we were to add these 2 things together? Let's add these equations and see what happens. Well, on the left side, well, on the right side, we do get the y2s cancelling out, which agrees with this guy over here. But the left side looks really suspicious. We can pull out a 3, right? By algebra, we can pull out a 3. And just like how the y2s cancel out, the x2s also will cancel out. And what are we left with? We're going to be left with 3 times x1 minus x3. And this guy is going to be the same as this guy. So we will get this equation, which allows us to deduce that the first and the last points are connected as well. And if they are connected, we can conclude that R is transitive. And that's how we show that R is indeed an equivalence relation. We have shown that it is reflexive, we have shown that it is symmetric, we have shown that it is transitive. And we can ask a very natural question. Now that we know that R is an equivalence relation, what are its equivalence classes? So B, what are the equivalence classes of each point under R, right? Under R. Right, so R, once again, is the collection of connections with the property that 3 times of x1 minus x2 equals to y1 minus y2. And we want to ask, what are the equivalence classes of UV? Well, whatever those equivalence classes are, it consists of points such that it's connected to UV, right? So we'll say, suppose that x and y and UV are connected. So if we can describe x and y in a considerably nice way, we will be able to obtain the expression. What this tells us is that 3 times of x minus u equals to y minus v. And this looks a bit suspicious. We can actually do a bit of algebra here, right? Let's do a bit of algebra. And we can obtain y equals to 3x plus v minus 3u. In fact, what that means is, well, for a point to be connected to each other, right, we must have that 3x minus u equals to y minus v. In fact, if 2 points are connected to each other, that means xy lies inside the equivalence class that contains uv. So we do see that xy has to lie inside a line with gradient 3, because that's the m, y equals mx plus c, and y-intercept v minus 3, well, 0, v minus 3u. So this tells us that every item in this guy will belong to this, and vice versa, because all the arrows are double arrowed. So every item in this guy belongs here. These two sets must be one and the same from our ideas of set equality. UV is the line with gradient 3 and y-intercept 0, v minus 3u. And that's that. It's a little bit tricky, but roughly speaking, that's the idea there as we unpack the definition of the equivalence relation. And part C is a little bit tricky, so let's see what we get here. So we probably will need this information. Let's use part C. Proof. Here's our claim. We claim that for any point UV, there exists some real number C with the property that 0C lies inside, well, 0C lies inside this equivalence class. So that's the claim. The claim is that we can always find a C. If we think about it, we sort of obtained our answer just now. Because UVR is the line with gradient 3 and this y-intercept, right? Isn't this a real number? Isn't v minus 3 a real number? That could be our C. So here's how we can prove it. Fix UV in R squared, we'll choose C to be the real number V minus 3U. Well, we know that this is a real number. Then 0C is by definition 0V minus 3U, which is the point with x coordinate 0 and y coordinate V minus 3U. That's the y-intercept of the line. So it must belong to the line. But the line is precisely the equivalence class. So it's a little bit tricky, but roughly speaking, that's how we can think about it, right? For any UV, we must find some C such that that's the case. I think that we could draw a few pictures, but I think this is pretty comprehensive. Now, we've seen that items in a box are sort of treated as the same, but we might want to prove that. So let's go ahead to prove this really useful equivalence relation property. We'll let this be an equivalence relation on a set A, and we claim for any x and y in A, and it could be the same items, we don't know and we don't care, x and y are related precisely when the equivalence classes are the same. X and y are related precisely when these are the same. So let's go ahead to prove this result. And in order to prove this result, we need to go in two directions. So let's first go in this direction. So we're just going to go in this direction first. So we'll suppose x belongs to y. What we need to do here is to see how to make the argument work. We claim, this is our goal, right? Our goal is to show that x is equal, the class containing x is the class containing y. This is an equality of sets. So, to do equality of sets, we need to show that we get double-sided inclusion. We need to prove that we have this double-sided inclusion. How do we go about this? Let's first go ahead with this guy and let's see what we get. Let's fix any item we wish. And we've used x and y, so let's use, say, r inside x. We want to show, hopefully, our goal is to show that r belongs to y. We want to prove this result. This will help us establish the subset connection there. Okay. How do we start? How do we start? Well, now if R is in the class containing X, then R is by definition gonna be related to X. But if R is related to X and X is related to Y, then we can say that R is related to Y. Let's justify this statement a little bit more precisely. Because X is related to Y and this symbol, this relation is transitive. This tells us that R is related to Y, which means that R belongs to Y, and we have the first subset connection there. Now, what about the second one? Now, the second one feels a little bit strange, but I think we can... I want to try to cheat. I want to try to cheat here. So we'll fix... Say, we'll fix R inside the second guy. Let's follow the same train of thought. This tells us that R is related to Y. And just like before, we want to say that X is related to Y. But how do we make the connection? Well, we have that. We want to say that R is related to X. And we want to make this connection similarly, just like before, because the relation is transitive. And at the same time, we would like to have the result that y is related to x. Well, a priori it doesn't seem to be the case, but actually we do get this result because this guy is symmetric. And that's that. So I believe there's a shorter way to prove this, but it's fine. We can just use this. But this is fine. So that has helped us establish that we get, well, the first part over here establishes this subset relation over here. This part over here tells us that every R inside the class containing Y belongs to X. Well, it's related to X, which means that, let's try that again. R belongs to the class containing X. We obtain the second result. And we've proven one direction. We need a bit more effort. So let's go in the other direction. Let's go ahead and prove this direction. Let me clean up the board so that we can prove the other direction. Now let's go the other direction. And we need to suppose that X, the class containing X, is the class containing Y. Then we want to show that X is connected to Y. X is related to Y. It almost feels obvious, right? Because, okay, let's see what does this mean. If X is related to Y, we need to show that X lies inside the class containing Y. But under this supposition, under the supposition that these two classes are actually one and the same, we need X to be connected, well, we need X to be inside its own equivalence class. Now that feels almost obvious, but let's give a quick proof. We know that X is related to X because this guy, the relation is reflexive. And if it's reflexive, then the element X is related to itself, which means that it lies inside its own class. And because the class containing X is the class containing Y, X lies inside the class containing Y, which means that X is in fact related to Y. So it's a short proof, gets the job done, works out pretty well. I had no idea why I had to clean up the space there, but it is what it is. It's fine. Equivalence relations are nice in that regard. They have these really nice clean properties. So we've seen a bunch of proofs pertaining some of the properties, and we have a sort of conjecture that might naturally arise when we think about the connection between symmetry and anti-symmetry. So we have a claim here that every relation that is both symmetric and transitive must be reflexive. And we have a few more claims which we might want to try to prove or disprove as well. So let's go ahead to try to, well, prove this result. Well, not prove this result, but this is the claim, and turns out that this claim is actually not true. It might feel very natural. Okay, so let's just look at the proof and see what result are we actually proving here. So if we have a relation that's symmetric and transitive, we want to fix X inside the set, well, let's just say on A, just so that we can put in the A over there. It's a technical importance. And let's suppose that we can find some y in A with the property that x and y are related. Let's call this relation R. Then we do have symmetry, right? So by symmetry, so this gives us, by symmetry, that we can flip the y and x's around. And because we have x and y being connected and y and x being connected, these two things, well, I'm going to put it here. By transitivity, these two things will give us that x is connected to x. So therefore, x is reflexive. So this is our claim, but there's one subtle problem here. We actually included an extra assumption. So we actually do prove a partial result of this claim, actually. If we were to add in some extra conditions, so every relation on A such that for any x in A, there is at least one connection. If we include this condition, we actually do get a claim that is true. And we do get a proof. We do get a rather reasonable proof. However, if we were to omit this condition, then it no longer works. Well, it may not necessarily work. So let's try to find a relation, right? Let's see what happens. Here is my claim. Let's call this condition star. Omitting star, the conclusion may not. In other words, the conclusion may not hold, which means that R may not be reflexive. So here's the proof. Let's consider this following equivalence relation. I'm going to just draw a diagram here to illustrate the point. Here's 0, here's 1, and then we're going to draw a loop. Is it symmetric? Well, yes, every street is a two-way street. Is it transitive? Well, this is the only street, right? So the only kind of things you could get are the street, which lies inside. So we still get transitivity. But do we get reflexivity? This fails. We don't have reflexivity because we have found an item such that it's not connected to anything, not even itself. Not even itself, yes, it's not even itself. That's the funny thing, right? So this is a good attempt, but there is a little bit of a bug over here. Now we do have a few more interesting claims that are of the similar nature. Well, just what happens if you combine symmetry and anti-symmetry or vice versa and whatnot? Well, some people will claim that if we have, so we let R be a relation on A, then R is symmetric will imply, the claim is that R is symmetric implies that R is not anti-symmetric. That's one claim, and there's another claim which we'll take a look at in just a moment as well. So that's our claim, and perhaps we could probably derive something a bit similar to this claim. So firstly, suppose R is symmetric, we'll fix x, xy in A such that xy in R and yx in R. So the idea here is not necessarily that x cannot equals to y, but the idea of, well, actually yes, such that x is not equals to y. We actually need to impose this condition, right? So in other words, we can find well, let's do it this way. So we'll fix x and y, or rather, let's do it this way. We want to try to, under some conditions, disprove antisymmetry. So we'll say, suppose there exist x and y distinct such that x and y lie inside the relation. Right? So we can write it this way. There is this x and y with the property that x not equals to y and x and y being in R. Then, by symmetry, yx is in R, and these conditions altogether will violate antisymmetry. Because you're getting to get, you're essentially getting a two-way street. Now, what that means is that, again, if you suppose an extra condition, suppose there exists x and y, x not equals to y, and x and y are connected. Under this extra supposition, we do get the fact that R being symmetric means that R is not antisymmetric. This is our counterexample. However, what happens if we don't have this condition? The result may not necessarily hold as well. So once again, suppose star does not hold. Right, suppose star does not hold. What does that mean? Then let's consider a following relation here. Once again, let's use 0 and 1, like this. And this relation is symmetric because you get two-way streets. Every connection is a two-way street. It is antisymmetric as well because every street is a one-way street. We treat loops as one-way. So this relation is symmetric and anti-symmetric at the same time. And the reason why is because we do not have this condition. We actually violate this condition so that we do get the fact that R can be both symmetric and anti-symmetric at the same time. It's possible. Well, what about a different claim? Let's clean this up and let's ask maybe a slightly different claim. Can we show that if R is not symmetric, then R must be anti-symmetric? In other words, it's basically the inverse expression. Let's see if this could be the case. So to show that R is anti-symmetric, we probably once again will need to impose some conditions if we want this to be true. So let's see. Fix x and y inside A. We will suppose that they are connected. And we want to hopefully show that x must equals to y, one way or another. So once again, I believe here we do get the same property. So suppose there exists x and y such that, actually I'm not too sure what the condition here is. Let's think about it. Let's find conditions so that this holds. So what's the idea here? Well, the idea is that if we get symmetry, then we will get a violation, right? Roughly speaking. So we know that these two things are true. So let's try this. If x is not equals to y, okay, then so we know that there must be. Now, if for any x and y in A this holds, we will have R being symmetric, which doesn't hold. So therefore, there must exist Z in A such that either XZ in A or ZX in A, but not both. But not both. So what does that mean? Well, not in A, my goodness, this is in R. But not both. And what does that tell us? It's kind of weird because I'm trying to prove a result which doesn't really hold. I'm not too sure. I actually can't really find any conditions such that this is true. But let's consider a different. Let's first show that this result in general is not true. I would like to think that there is a condition which we can impose so that it becomes true. But let's first show that claim is false. Let's first show that this claim has to be false. So how would I go about it? Well, symmetry roughly tells me that every street is two-way, and anti-symmetric, roughly speaking, means that every street is one-way. So every street is two-way. Let's consider loops. So if it is not symmetric, means that we must have at least one-way street. Okay, here we go. There we go. So now we both have a loop. We have one two-way street, therefore it's not anti-symmetric. And we do have a non-two-way street, so it's not symmetric at the same time. Then R is not symmetric and not anti-symmetric. Right? It's symmetric and not anti-symmetric. So I think this is actually the condition here in order to go from non-symmetry to anti-symmetry is actually really strong. It's not entirely obvious what we need to impose in order to get that property. So we're not gonna spend too much time on that, unlike the previous versions. Okay. Let's talk about partial orders once again. And we want to show this little interesting result. My student actually gave me the proof for this, so props to, I think it's Vincent if I'm right. I think so. Yeah, for a very interesting proof. So we're gonna first let R be a partial order on the set A, and we'll suppose that there are no points with the property that x1 is not equal to x2 and x1 and x2 are connected, x2 and x3 are connected, so on and so forth, xn and x1 are connected. In the provided solution, the proof was by induction, which can be done, but it's interesting because we actually have a strategy which firstly does not require induction, secondly, the essence of the proof can be converted to the inductive argument. So here's our claim. Okay, so the claim, in fact the claim, this is our claim, that such a thing cannot exist. So it's really hard to prove a claim of non-existence. So I'm gonna go ahead and say that suppose instead there exist these guys with the property that x1 is not equal to x2 and x1, x2 in R all the way to xn, x1 in R. Maybe we'll put the second point for clarity. The second connection for clarity. And the goal is to derive a contradiction. That's our objective. It feels a bit strange, but the key trick here is to draw the points and hopefully find something that works out. So let's draw x1, x2, x3, and we have a few more points, xn minus 1, xn. And if x1 is not equal to x2, then it's different, but they do have arrows. So all these guys do have arrows like this. And one way or another, we need to find some contradiction. So how would I go about this? Well, if x1 is not equals to x2, and we have this relation, to violate anti-symmetry, I just need to show that we get a contradiction, because R is a partial order, right? R is a partial order, so R must be anti-symmetric. Right, that's what makes it special compared to the equivalence relations. So let's just start there. So since R is a PO, and we have that x1 is not equal to x2, and we have that they are connected, if x2 is connected to x1, we are going to have to, well, then the idea is that x2 cannot be connected to x1. If that happens, then we get a two-way street, right? If x2 is connected to x1, we will get a two-way street and we get violation. We violate the anti-symmetric property. Now, on the other hand, we have arrows in this way, which represents a partial order. And partial orders tell us that arrows are transitive, right? The connection is transferable. So since R is a PO, a partial order, so it is anti-symmetric here, which implies that this holds. But at the same time, R is a partial order, it is transitive, which tells us that when we combine all of these results together, when we combine these guys all together, we will get x2 being related to x1. Because we start from x2, we go to x3, x3 connects to x4, x4 connects to x5, and so on and so forth, all the way to xn and x1. I believe that's where the induction happens, this three-step transitivity. I think that's where it happens. But you can do it. We'll leave it as an exercise. You can check, right? You can check that this is the case. This is where I think the induction will take place. But what happens here? We get x2 being not connected to x1 and x2 being connected to x1. This gives us a contradiction. And since we get a contradiction, the initial claim must be true, because we've shown that the negation leads to a contradiction. Therefore, done. So, shoutouts to, I believe it's Vincent, if I'm right, for this proof. It's a really clean and elegant proof. Gets the job done, and I think it's really nice. We have some other, just to revise on the idea of partial orders and whatnot. We can revise that using some of the following questions: partial orders and equivalence relations. Let's revise using this question. Let's consider the relation that connects rational numbers via strict positivity. Now it's interesting because we actually did a question like this earlier on. There was a question similar to this, where we sort of had a property like this, but we didn't. But the bigger than is replaced with bigger than or equals to. So we've actually done a problem before, and you can go check it out. So let's take a look. Let's ask the questions. Is it reflexive? symmetric, anti-symmetric, intransitive? Which of these does it satisfy? Well, let's just slowly think about it. And the first thing to note is it might not even be reflexive. And the reason why is this, right? We're considering rational numbers, right? So for reflexivity or the lack thereof, observe that 0 is a rational number. And we know that 0 times 0 is equal to 0. This is actually, well, 0 times 0 is equal to 0, which is less than or equals to 0. So therefore, 0 times 0 being bigger than 0 is false, which means that 0, 0 does not lie inside the relation. We're not off to a great start here. But I think we get some other properties. So for symmetry, we have that, okay, we'll say fix x, y in Q, and we'll suppose that x, y lies inside R. To show symmetry, we hope that x, y, well, not x, y, y, x will belong to R. That's our idea. I think this is true, and here's how I'm going to argue it. If we decode this, we're going to get x, y being positive, but multiplication of rational numbers can be swapped. It's commutative, so we're going to get yx being bigger than 0, which gives us the result. So it is not reflexive, but it is symmetric. For anti-symmetry, I think we can easily violate this by choosing 1 and 2, which are both rational numbers, and 1 is not equals to 2. Then we have that 1 times 2 is 2 times 1, which is positive, which tells us that 1, 2 lies inside R and 2, 1 lies inside R. Again, we have a two-way street, and therefore it is not anti-symmetric. Now, transitive is the one which I'm thinking about. I think it's true, and the argument is not as obvious. So for transitive, we're going to fix x, y, z inside Q, and we're going to consider, we'll suppose that x, y is bigger than 0. Well, x, y are connected, and y, z is connected. Now I think it's transitive, so let's write out what these definitions here mean. And my idea is this. If you combine these two items together, you're gonna get xz y squared z being bigger than 0. So sort of like one of the problems that we've attempted before. However, we need to get rid of the y squared, and I need to make sure that this y squared is, well, y squared is non-negative. So the symbol, I think we can say that the symbol will go away, but even then, I think we need to make the case. We need to be careful here. I think this is how we're gonna do it. Now, I'm putting extra z there, darn it. Now, we know that this is a product of two terms. We have a product of two terms here, and the product of two terms is non-zero. It's bigger than 0, in fact. So this tells us that whatever these two terms are, neither of them can be 0. Now xz, we don't know whether it's negative or not. I mean, there's just not enough information. But y squared is an interesting case, because on the other hand, we know that y squared is always non-negative for any rational number y. But if we were to add the condition, were we to build on that the condition that it's non-zero, we must have y squared can only be strictly positive. Now that's important for us because now, because of this property of positivity, we can divide out the y squared and conclude that xz is positive. We can divide out the y squared because it's non-zero, and because it's positive, the symbol remains the same. So we do get xz being bigger than 0, and therefore r is indeed transitive. So it's a little tricky, but it can be done. Let's consider the relation S defined on the integers. And we will define this connection via y equals to x plus 1. This is the connections which we are going to concern ourselves with. And once again, we're going to ask the questions. Is it reflexive, symmetric, anti-symmetric, or transitive? That's a curious question to ask there. So let's see. For reflexivity, it's actually quite unlikely, right? Because if you sub in zeros, 0 is not equal to 1. So since let's consider x equals to 0, well, then we see that 0 is, and 0 plus 1, on the right side we get 1, but 0 is not equal to 1 in the integers. So 0, 0 does not lie inside S. I think symmetry doesn't work either, so we've seen that reflexivity doesn't work, but I think even symmetry gets violated here. It's kind of sad, but it is what it is. So for symmetry, let's consider 0, 1. Let's consider x equals 0 and y equals to 1, both integers. Then we do get 1 being equal to 0 plus 1. But sadly, if you flip, obviously 0 is not equal to 1 plus 1 because 0 is not equal to 2. So 1, 0 cannot lie inside S, which means that it's also not symmetric either. Not off to a great start, but it is what it is. For anti-symmetry, we actually get something really interesting here. I think the answer is true, but here's sort of the justification. So my hunch down me is true, but here's why. So we'll suppose, or rather we'll fix x and y in the integers, and we need to suppose that xy lies inside S and yx lies inside S. There's only one slight problem. You cannot have these two things happen at the same time, right? And the reason why is because this means that y equals to x plus 1. This means that x equals to y plus 1. If both things happen at the same time, what are we going to get? Well, we could do a bit of algebra, and these two things will combine to give us x equals to x plus 1 plus 1, so that's actually x plus 2, and 0 equals to 2, a contradiction. So it's not even possible to begin with. This situation is not even possible. But the anti-symmetry condition tells us if this happens, we ought to get x being equal to y, for example. But if this condition doesn't even happen in the first place, then we're going to get false implies true as a whole. And therefore, we get anti-symmetry vacuously because the statement xy in S and ys in S implies x equals to y has the truth value. False implies whatever, who cares, no one really cares, which evaluates the true. So it's ironic because even if you fix x, y, and z, this entire implication still is true vacuously. And that tells us that anti-symmetry still works. Vacuous truth is still truth, even if it's not the most useful piece of information. So that's rather surprising. Now let's clean the board and check the transitivity, if there is, between x and y. In fact, I don't think transitivity works. So yeah, I don't think transitivity works. So let's show that it doesn't work. So let's choose x equals to 0, y equals to 1, z equals to 2. Then we know that 0, 1 lies inside S. And similarly, 2 equals 1 plus 1. So this guy lies inside S. But 0 is obviously not equals to 2 plus 1. or rather, 2 is not equal to 0 plus 1. Sorry, 2 is not equal to 0 plus 1 because 2 is not equal to 1. So the connection is not transferable. And therefore, it's not even transitive at all. It's kind of sad, like this particular connection is not exactly the most user-friendly one, but it is what it is. So we've talked about a relation being symmetric, transitive, and whatnot, using the definitions. Turns out that there's another way we can talk about a relation being symmetric and transitive using some relation properties. So we're going to find a secret hack about transitivity and symmetry. So we'll let R be a relation on a set A. I don't really think we need A in this context, but let's just use it. So here's our first claim. R is transitive precisely when R circle R is a subset of R. This is a rather surprising result. It's like, wait a minute, like, huh? We can talk about transitivity in terms of relation composition? Yes, we can do that. So let's prove it. Let's go in two directions, just like before. So we'll suppose R is transitive. And what we need to do here, we need to prove that the left side is a subset of the right side. So we need to fix an item inside the left side. And our goal is to show that it belongs to the right side. So let's work our way through. Since xy belongs to the composition, we can find a bridge. Yes, back to our bridges. Yes, we can find a bridge inside the set A, because R goes from A to A, such that xz belongs to the first guy and zy belongs to the second guy. So x can go to z and z can go to y. But we have R as being transitive, right? We know that R is transitive. So we can combine these results to get xy being inside R, which is our goal. So we have done it. We've actually proven this result. And now we need to go in the other direction. Well, other direction. Okay, so let's go in the other direction. We will now suppose R circle R is a subset of R. We want to show that R is transitive, so we need to fix a bunch of items. well, I guess we can be a little bit more precise there. We will fix x, y, z in A with the prop and suppose that x, y are connected and y, z are connected. Our goal is to show that x, z is connected. So what do we have here? Now, because x, y, and y, z are connected, y serves as a bridge from x to z. So since y serves as a bridge by the definition of function composition, xz must belong to the composition of R with itself. But we've seen that R circle R is a subset of R, and so we have xz being in R, which is the goal that we wanted to derive. So we've proven both sides, and we've actually proven this result. This is to say that a relation is transitive precisely when the composition with itself lies inside R. It sort of remains inside the same relations. Really, really cool feature here. Do we have a similar idea for symmetry? Turns out we do. So let's clean up the board and write out our new claim. Let's claim now that R is symmetric precisely when it equals its inverse. Whoa, where did inverse relation come from? We define the inverse relation to be all of the flipped connections. So that's pretty interesting. So let's go ahead and prove it. Once again, we need to deal with two directions. So let's go ahead in the first direction, this way. So we'll suppose R is symmetric. And we need to ask, what do we need to prove? We need to prove that these two sets are equal to each other. Equality of sets means we need to prove that both inclusions hold. And let's just hope for the best. Let's fix x, y inside R. And in order to derive this result, we need to show that xy belongs to R inverse. Now for xy to be in R inverse, we need to have that yx is in R, because that's what it means for an item to be in the inverse. It means that the flipped version is in R. So do we get this connection over here? Yes, we get this connection because R is symmetric. If R is symmetric, then if you go from x to y, you can go from y to x. Pretty cool feature here. So we get the first result over there. And similarly, if you start out with x, y inside R inverse, you're gonna get yx in R, which means that xy in R by symmetry, which gives us the other subset inclusion, and we have proven the first direction. All that remains is the second direction. So let's go to the second direction. I'm gonna risk and not clean up the board because I think we can finish it here. So let's suppose R equals to R inverse. We want to show that R is symmetric, so we'll fix x, y inside A and suppose that x, y is in R. What's our goal? Oops. Our goal is that yx is in R. And the flip picture here tells me I should probably write this as xy in R inverse. So do we get this property, xy being in R giving us xy being in R inverse? Yes, under the assumption that R equals to R inverse. And that's that. We're done. So that's a really cool, neat result there, where we can talk about symmetry using these relation properties, or rather using the relation itself rather than having to formalize it using some English words. Let's do a final exercise on proving equivalence relations. So we want to define the relation R on A, or rather on the integers, by connecting two integers under the condition that the difference is even. We claim that R is an equivalence relation. So how do we prove this claim? To prove this claim, we need to check three things: reflexivity, symmetry, and transitivity. So let's check reflexivity. So do we have, let's fix x in z. Our goal is to show that x is connected to itself, and that means that x is... My brain stopped working there. Whoo! It means that x minus x is even. But that means that... is that true? Well, yes, because x minus x is 0 is even. And I'm so tempted to just go ahead with the definitions, but I realize we have a shortcut for the remaining two properties. Now for symmetry, you can go check out the previous video that we did. We've already proven that R circle R is equal to R. We've already proven this result, and this is a rather surprising result. It's quite interesting. But if equality holds, then the subset relation holds. I realize this should go here. And if the subset relation holds, by our previous transitivity hack, we automatically get R is transitive. Because what have we shown just now? We've also proven previously, I think this is question 9, that R is transitive precisely when the composition lies inside itself. And we also have R is symmetric precisely when the inverse equals itself. But we've also shown in the previous video, stream, whatever, that R is equal to R inverse, which means we can use the result, rather ironically, that R is symmetric. So ironically, we've already done all the hard work needed to show that R is an equivalence relation. It's kind of strange that we could just use all of our previous results to solve this question. Now, if you want to see what these previous results are, you can go check out the videos on the screen somewhere, somehow, and knock yourself out over there. But then that raises another question, which I'm just gonna try to put it all on the same screen because why not? What are the equivalence classes of X? So what are the equivalence classes of X? So if you have an integer, what are the equivalence classes? We'll think about it as, okay, so we'll say R is inside the equivalence class precisely when R is related to X, precisely when R minus X is even, which means that if the difference between two numbers are even, they are either both even or both odd. So in other words, R has the same, what we call parity. Parity means either even or odd, as X. And since every integer is either even or odd, we are going to get the equivalence classes 0, that contains all of the even numbers, and 1, which contains all of the odd numbers. These will give us, these are the equivalence classes with respect to R. These are all of the equivalence classes that we get. The first one gives us all of the even integers, and the second one gives us all of the odd integers. And that is how we derive the equivalence classes in this context. I believe if the condition is not x minus y is even, but say a multiple of 3 or whatnot, we will get different equivalence classes. With respect to this particular relation, we do get these equivalence classes already. And that's it for equivalence relations and partial orders. We will definitely see more of these in the coming days ahead. For the next stream, we will be looking at functions, and this is where things get a little bit tricky. Functions are important because we're gonna use functions to talk about cardinality and countability, which are highly non-trivial ideas. So see you guys in the next one.